Good morning and welcome to this plenary talk of the International Material Research Conference. We welcome those of you here in the audience and those of you watching us via YouTube and the streaming services. The last plenary speaker of this conference is in charge of Professor Susanne Stemmer. I will be presenting here on behalf of Berly Kempen. She has a schedule problem and has to leave earlier. So let me read some brief lines about Professor Stemmer's work. She is a professor in material science at the University of California, Santa Barbara, and she's in charge of the quantum materials lab. Her work focuses on quantum materials, heterostructures, and advanced characterization techniques. Currently, she's interested in functional and correlated oxides and topological materials, and today's talk will be around topological materials. And besides her astonishing scientific production that has landed her several awards, such as being Fellow of the American Physical Society, the Material Research Society, the American Ceramic Society, and the Microscopy Society of America. So it is for us a true pleasure to have Professor Stemmer. She will be giving the closing plenary talk of this 29th International Material Research Conference. Thank you, Susanne, for accepting this invitation, and let's welcome Susanne.
Thank you very much for the nice introduction. I also wanted to really thank the organizers for inviting me, and I'm really sorry that I cannot be there in person. I was really looking forward to this meeting. Can you see my slides? I assume you can see the slides. So let's get started. So I will be talking about a topic that is ongoing research in my group that we started around 2016, and it focuses on heterostructures with topological semimetals. So before I start, I would like to acknowledge the people who actually did the work. In particular, Manik, Timo, and David, who were really the one who started the growth of this topological semimetal by molecular beam epitaxy in my group. I will also talk a little bit about the work from Omar Shoron, who worked on transistors with these materials. And you will also see some nice transmission electron microscopy images. Those were taken by Salva and Tyler, Salva just left my group. And Tyler is still a graduate student in my group. And also I will show some work from Luca Galetti, who was a former postdoc in my group. And of course, I would like to acknowledge the funding agencies that funded the work. In particular, we pretty much started all of this primarily with the Vannevar Bush Faculty Fellowship from the DoD. And then the transistor work that I will be showing is work funded from the Army Research Office. So brief outline of my talk is I'll first introduce what are topological semimetals. And for those of you who are not so familiar with these materials, I will then proceed to talk about our work and how we grow these films. In particular, I will focus all of this talk on one material, cadmium arsenide. We use molecular beam epitaxy to grow thin films of this material. And I will show you a little bit how we can use thin films, for example, strains in thin films, to obtain different topological phases in these thin films and heterostructures. And I will talk about the interesting surface states that these materials have. And then I will talk about more practical applications, in particular applications for high frequency applications with these materials. Oops, sorry. Right. So to introduce topological semimetals, this table here shows the larger family of Dirac materials, which contain some of the very famous materials such as graphene, which is a two-dimensional Dirac material, and other related materials, and also, for example, topological insulators. Famous ones are bismuth selenide, strained mercury telluride. These are 3D topological insulators, but there's also materials that are called 2D topological insulators. And then later following the discovery of these materials, around 2012 and 2014, the first theoretical predictions and then very shortly thereafter experimental realizations of a group of materials called three-dimensional Weyl or Dirac semimetals. And one of the first materials that were actually investigated in this group of materials was cadmium arsenide. This is the material that I will talk about, and another material, sodium bismuthite. What are these Dirac and Weil semimetals? So the easiest way to understand is to look at a material, and this is from Claudia Fels's very nice review article that I can recommend everybody to read, is if you have a material with a band inversion. So here in a certain part of the Brillouin zone, there's an inversion between what are normally the conduction and valence bands in this part here. And normally this is not stable, so spin-orbit coupling usually opens a band gap. So we have still this inverted structure, but we have a gap opening here. And this is what results in a three-dimensional topological insulator. But if there's, in certain materials, and these are the Dirac and Weil semimetals, there are certain crystalline symmetries that prevent a band gap from opening in certain points in the Brillouin zone. Okay, so and around these points, these touching points, so the Dirac nodes or Weil nodes, you have a linear energy dispersion, and you have this linear energy dispersion in all three dimensions. So unlike graphene, so they're sometimes considered to be the 3D equivalents of graphene, you have this linear energy dispersion around these nodes in all three dimensions. So the important part about this is that what's often very important in these materials is certain crystalline symmetries that protect these nodes. And then conversely, and this is a theme of my talk here, if you, for example, break these symmetries, in cadmium arsenide, it's a fourfold rotational symmetries, you get a band gap and you get a topological insulator. Okay, and you can see where this is going with thin films. We can of course use thin films relatively easily to, for example, break rotational symmetries. So the first materials in this class of materials were predicted theoretically in 2012 and 2013. I've listed some of the key papers here. And then very quickly experimentally, people synthesized these materials and confirmed that they were indeed these three-dimensional Dirac materials using ARPAS studies. Right. So there's other interesting, besides the Dirac nodes and the linear energy dispersion. I'll get back to this. But from what I already sort of alluded to with breaking symmetries, a very interesting property of these Dirac semimetals is that they're actually close to a number of other topological phases. So as I mentioned, for example, if you open a band gap, you very often get a three-dimensional topological insulator state. And so what is a three-dimensional topological insulator? That's a material where there's a band gap in the bulk, but the surfaces are actually conducting. And the surfaces, again, you consider them to have Dirac nodes on each of the surfaces. And interesting properties such as the spin momentum locking that I've tried to indicate here. You can, of course, also get trivial insulating states. I will not talk about those. If you, for example, break a time reversal symmetry or inversion symmetry, and then you split these degenerate Dirac nodes into two, and what you get is a Weil semimetals. Those are also very interesting because they, for example, also their own very, very interesting surface states, and I come back to that. If you take this 3D topological insulator state and make this very, very thin, predictions, and this has not been shown to my knowledge, what you should actually then end up with is a two-dimensional topological insulator that is without any application of a magnetic field, has these edge states that are very similar to the edge states, somewhat similar to the edge states in a quantum Hall effect, but without a magnetic field. Okay, so what you also see from this is that thin films should be very interesting because in thin films we can break these symmetries, and of course in thin films we can make thin things. Confinement, making quantum wells out of materials is what thin films obviously are good for. So there's an interesting starting point here with these Dirac semimetals to obtain a number of other topological phases, and I will focus in this talk particularly on the 3D topological insulator phase. With this material cadmium arsenide. Right. So cadmium arsenide, a little bit of history because it's kind of fun. It was actually discovered way back, and what was noted immediately was that it had a very high electron mobility. And so now we understand that it is due to its special electronic structure belonging to the Dirac materials class. But in this case, it's way back, it was not quite understood, but it was already realized that this is potentially for high mobility applications, which of course is very useful for electronic devices, an interesting material. So then more recently, so starting in 2013 with this paper, it was predicted to be a three-dimensional Dirac semimetals. And here I show the results from electronic structure calculations. And what you can see here is indeed, just like the cartoon picture that I showed you earlier, there's this band crossing here. And the good news about cadmium arsenide, it's right at the Fermi level. And in cadmium arsenide, this is also a relatively simple version, because in the sense that that we only have two of these Dirac nodes that line up along this fourfold rotational crystalline symmetry axis. Okay, so that has only two of them, so that makes things relatively simple, and they're right at the Fermi level. There's another interesting property, and I come back to this, is that it's the crossing is actually by mostly arsenic 2p states, and very way down, but at the gamma point, we have this cadmium S states, and so the band inversion is between these 2p states and cadmium S states, and it's very, very large. So later, when we open a band gap, for example, by breaking this fourfold rotational symmetry, we still have this very large band inversion. And via the bulk boundary correspondence, and I talk about this in just a second, that dictates that we have a topological insulator states with topological surface states. Okay, so the gapped phase, so see, even if we would open a gap here, is a topologically non-trivial phase. And this is also very nicely described in this original 2013 paper. Right, so the crystal structure is quite complicated. You can consider it to be an anti-fluoride structure, based on an anti-fluoride structure, where 25% of the cadmium sites are not occupied. And that makes this, so this is the outlined part here is the anti-fluoride unit cell with the missing cadmiums. And that's repeated throughout with cadmiums missing at different positions, and it makes this very, very large unit cell. And the other thing I wanted to mention here, it belongs to this point group here, which is space group, which is a 4/MMM point group, and that's a centrosymmetric point group. So it's not a Y-semimetal because it has a center of symmetry. So the interesting thing about these topological materials is that there's a bulk, what people call a bulk boundary correspondence, and that's illustrated here in a very cartoonish way. So I've illustrated here these the bulk Dirac nodes as these orange dots here, and depending how they project on the surfaces, you get different types of surface states. So in case where, and this is so except for the 001 surface, so these two Dirac nodes line up along the 001 direction, and where they project on a point on the surface, all the other surfaces, they project on separate points in the Brillouin zone of the surfaces. And what you get in these cases are these Fermi arc type of surface states that connect the projections of these bulk Dirac nodes. Okay, so there's surface states on all the surfaces, but the 001 surface, which I will talk about later, is a little different. It does not have these Fermi arc structures. Okay, so, and as I mentioned already, if you confine them, for example, along the 001 direction and open a gap, the predictions to get a 3D topological insulator, and I will show you that this is indeed the case. And if you would further confinement, you would get this quantum spin-Hall insulator. Yeah. Okay, so now that I've talked a little bit about all the potential topological states that we can obtain using cadmium arsenide thin films and using strain engineering and confinement, here's a little bit of just an overview where things stood in 2016 as far as thin films of this material are concerned. And so basically there were no epitaxial films in 2016. and they were put on often on substrates where you would not expect glass or quartz or something, where you would mica, where you would not expect an epitaxial film. But despite this, the mobilities were actually quite high. So these are room temperature mobilities here, and for non-epitaxial polycrystalline films, these are actually quite respectable mobilities. But compared with what we would expect from cadmium arsenide, these were moderate mobilities. There were no electric field gating studies, no heterostructures, no devices or device fabrication beyond sort of measuring mobilities. So this is where the things stood. And so what we started out with is then growing these cadmium arsenide films by molecular beam epitaxy, mostly for the usual arguments. MBE is a technique where you get high purity films. It's a low energetic deposition technique, and we expect to synthesize fairly high mobility films with that technique. So what we do, the way we grow it is we grow it on 3-5 layers, 3-5 semiconductor layers, which I will show you in a minute. And what we do is we simply evaporate the compound itself, cadmium arsenide. Okay, so it looks relatively simple. It turns out the growth of cadmium arsenide is relatively straightforward, but there are other problems, and they are related to the substrates. Okay, so cadmium arsenide, as I mentioned, has a very large unit cell, and it has a very large. The pseudo-cubic lattice pyramid is very large compared to the substrates and buffer layers that we are using, which are these 3-5 semiconductors. So here's cadmium arsenide. The equivalent lattice pyramid is 6.3 angstrom. And you can see that this is rather large for the typical 3-5 semiconductors that we have. So we have, to mitigate the very large lattice mismatch with substrates such as gallium antimonide, we actually very often grow lattice matched buffer layers, but I show you some of the problems with those. Okay, so this is generally not easy to grow 3-5 semiconductors that we are using here as substrates and buffer layers with these lattice parameters. The other difficulty is that cadmium arsenide likes to grow in a 112 plane. That's the low energetic growth plane. That is the equivalent in a cubic structure would be the equivalent is the 111 plane. That's not a common growth orientation for 3-5 semiconductors, so we had to develop the growth of 111 oriented 3-5 semiconductors. There's not all that much in the literature about that in order to get a suitable growth surface for this cadmium, for the easy growth direction for cadmium arsenide. In the meantime, we also then developed later, we also developed 001 growth of cadmium arsenide in the 001 direction on 001 surfaces. That's a lot more difficult, and it doesn't grow quite as well as the 112 direction. Okay. On the other hand, the 3-5 layers grow better in this orientation. So just to point out again, so we'll talk about these two orientations, 001 films and 112 films of cadmium arsenide. 001, as I mentioned before, is the one where we do not expect these Fermi arc states, okay, because the bulk nodes project onto a point under the surface, versus 112 is one of the surfaces where we would expect these Fermi arc type of states. So there's a difference in the type of surface states that we would expect for these two different growth orientations. So it's very suitable to look at differences in orientation and how they matter in the electronic and transport properties of cadmium arsenide thin films. So these are some early results of the growth of cadmium arsenide thin films in the 112 direction. So this, as I mentioned, is the easy growth direction for cadmium arsenide. What you can see here, these are the growth temperatures. They're very, very low. So it grows at very low temperatures. It grows very nicely, which you can see. You can get streaky read. You can get thickness fringes, and you can get atomically stepped surfaces in this growth orientation. And we can also, this is a cross-section TM image here on the right. You can also get fairly thin films of cadmium arsenide. So in this case, the heterostructure was a gallium arsenide substrate and a gallium antimonide buffer layer and then a cadmium arsenide. And what is also encouraging is that these are room temperature mobilities for these different growth temperatures. So they're close to 20,000. So this is quite high, quite a high mobility. Okay, so this was encouraging for the 112. As I mentioned, the 001 orientation is a little bit more difficult to grow. But David, the student who did this work, managed to grow this by using a wetting layer of indium arsenide, and then it grows a little better. And then later we also grew it on lattice match. That's a lattice match buffer layer, and you can see the cross-section, high resolution cross-section TM images here, atomic resolution images showing that we have also grown the cadmium arsenide in the right crystal structure, and that's a image of the surface. So it's fairly smooth. It's not as atomically stepped as the 112 surfaces, but it's fairly smooth. Okay. So here's just an example of microstructures, and in particular for the 001 films. And what's shown here in the cross sections here, so this is a different buffer layers, and their lattice match, the lattice constant, which I mentioned, to cadmium arsenide, which I mentioned, is difficult for 3/5. And you can see why it's difficult. You can see these are grown in gallium antimonide substrates, are very heavily dislocated. Okay, as you grow very thick buffers, the dislocation densities are being reduced by dislocation reactions. But the good news about the whole thing is that the cadmium arsenide contains significantly fewer dislocations than the 3/5 buffer layers, and that has something to do with the large unit cell, which has so cadmium arsenide also has then a very large Burgers vector, and it keeps these dislocations from going into the cadmium arsenide films. Nevertheless, what you do to the buffer layer matters. So for example, here's a thin buffer layer, and there we have a high dislocation density in the cadmium arsenide. If you use thicker buffer layers where we have fewer dislocations in the buffer layers, we also get fewer dislocations in the cadmium arsenide. Okay, so these are sort of the challenges if you work with mismatched substrates. In this case, the lattice pyramid of gallium antimonide is quite different from the buffer layers, and so these are the very typical challenges with epitaxial growth on mismatched substrates, and we suffer from the problem of not having a lattice matched substrate. So interestingly enough, and this is just data looking at mobilities for essentially these very same films here, and if you make the cadmium arsenide films very very thin, we get mobilities here about 40,000, which is quite good. And then interestingly enough, even if you have these very heavily dislocated buffer layers and a thin buffer layers where we'll have lots of dislocation in cadmium arsenide, and a case where we have a thicker buffer layer thicker buffer layer with a few dislocation in cadmium arsenide, the mobilities are actually not that different. But if you make them thicker, they actually get better. So there's a challenge with making thinner films. But the dislocations are pretty high. Okay, right. So next part of my talk is looking at how can we tune these different topological states, which is what I showed you in the introduction. So right now we have grown thick films of a Dirac semimetal, and the question is, can we go to any can we break, for example, fourfold rotational symmetries? Can we confine them? And can we get to these different topological phases that way? So the first example I will show you is using epitaxial strain. Okay, and so what's shown on this slide is 112 oriented films. And what we use as a technique here is convergent beam electron diffraction. That's a technique that is that can actually determine point groups. Okay, so these are experimental. These are all experimental convergent beam electron diffraction patterns. On the left, you see the results. So this is along different zone axes. So looking along different directions of these samples films. And this on the left is you see a relaxed film, unstrained. And what we found here from analyzing these patterns is that the point group is 4/MMM. That's a centrosymmetric point group, so we have the Dirac semimetal. Okay, then we can take this film and use our buffer layer to have a lattice parameter so that the cadmium arsenide is under compressive strain in this case. So given that the film is 112 oriented and the fourfold rotational symmetry is inclined in the film plane, as soon as we apply a biaxial in-plane stress, here we would expect that this four-fold rotational symmetry does not exist anymore, right? So this is something that you would just expect based on basic consideration, and this is exactly what we find. So we lose the four-fold symmetry axis, and our point group is MMM. That's also rhombic point group. So given the fact that we have here lost our four-fold symmetry axis that protects our bulk Dirac nodes, this film is expected to be a 3D topological insulator. I don't show you the experimental measurements, but that's indeed the case. So now let's turn to the 001 film. So in this case, the four-fold symmetry axis is normal to the film plane. So if you apply tensor or compressive stresses in the plane, you wouldn't expect to lose the four-fold symmetry axis, and indeed, we do not lose it from analyzing these patterns here. And a compressively strained film is, as expected, is in the same point group as a unstrained film, 4/MMM. The surprise came with a tensile strained film. That actually, and you can see this. So these four diffraction patterns are from the tensile film. These are from the compressive film. You can see you have in this pattern here, you have these two mirrors. You lose one mirror in the tensile strain film, and what that means is that actually it has lost an inversion center. Okay, and so remember, loss of inversion symmetry normally would get you a Wahl semimetal. In case of cadmium arsenide, it's a little bit more complicated. This shows the surprising result that tensile strained films lose the inversion symmetry. Compressively strained films along the 001 direction do not lose the inversion symmetry. What that means in practical, so this is not this was an unexpected result. What that means is actually that the unstrained material is already pretty close. The energy between these two, with and without inversion symmetry between these two different structures, are actually very close. And in terms of the atomic structure, what it means is that it's very, very subtle arrangements of the relaxations of around the cadmium vacancies. That's the difference between these two structures. And it looks like they're energetically very close. And so a small tensile strain then causes this inversion symmetry broken structure to be the preferred one. Yeah, so that's a sort of, as far as thicker films are concerned. So let's turn a little bit, so we use strain, let's turn a little bit to what happens in thinner films. And the idea is that we have thin films where we have a gap bulk, and that lets us more easily, so then in transport studies, we don't have too much bulk parallel conduction, and we can isolate the transport from the surface states. Right, and so this is the results that are shown here. So we look at rather thin films of 112-oriented cadmium arsenide films, so they're between 20 and 10 nanometer in thickness. And what we observed in this case is a quantum Hall effect. Okay, so these are grown on two different substrates in this case, but they're both 112-oriented. And in both cases, the results look very similar. There's a clear quantum Hall effect, and that means there's a two-dimensional electron system. And that means the box, there's no parallel, there's also very little parallel transport from the bulk. There's only transport from these two-dimensional states. And we get, and these two-dimensional states are in the surfaces. And that, for example, you can see, I don't show all the studies, but here, for example, if you look at this function of thickness and you compare the Hall carrier densities, these are carrier densities from the quantum oscillations. But you see the Hall carrier densities, as you have thick films, are fairly large. We make the films thinner, the films gap out, we lose the bulk carriers, and the only remaining carriers are those in the surface states. And those are the ones that give rise to the Shubnikov-Haas oscillations. And those, so for thin films, the two carrier densities agree, which means all the carriers are in the surface states. Okay, so that's one way of showing that these carriers, these two-dimensional carriers, are really in the surface states. Okay, and so these are probably from these Fermi arcs or Fermi loops, or residuals of those at least, that reside on these surfaces. So there was other groups that also, and I've referenced some of them here, that also saw this quantum Hall effect, and it was not really from this 112 cadmium arsenide fit, and there was not much agreement in literature about the origin. So one suggestion, for example, was that these are due to Weil orbits. Weil orbits are where these Fermi arcs connect through the bulk of the film, connect these top and bottom surfaces. That's unlikely in our case because I just showed you the bulk is gapped out. But also a suggestion was that we would have quantum confined bulk states. So these are really subbands as you would find in a quantum bell. And our interpretation is that these are the topological type of surface states. So to sort this out, it's easier to go to the 001 cadmium arsenide surface where we should not have any of these Fermi arc states that immediately should rule out any Weil orbits. So the two remaining possibilities, what the quantum Hall effect in these thin films could come from, are from a quantum confined bulk states or the 3D TI 3D topological surface states. And I will show you that this is the correct, the last one is the correct interpretation by doing two different kinds of experiments. So the first experiment is, again, looking at the quantum Hall effect as a function of in a gated Hall bar structure where we modulate the carrier density in the cadmium arsenide surface states. And the results are shown here. So these are all, each of these traces in this graph in the middle here of the slide are different gate voltages that correspond to different carrier densities. And what you get is a quantum Hall effect that is quite unusual. And it's quite unusual in the sense, for example, if you look at the first trace here, okay, what you, for example, see is a very strong nucleus 3 Hall plateau here, and almost the nucleus 2 is almost not present, okay? Versus at other gate voltages, you, for example, get a nice nucleus 2 plateau, okay? And also nucleus 3, and in some cases, nucleus 3 is almost absent, okay? So there's no obvious degeneracy. A typical lifting of a degeneracy would mean that the nucleus 2 is much more pronounced than the much more prominent than nucleus 3, and that's clearly not the case here. Okay, so often the higher filling odd news like this nucleus 3 is stronger than the next even like this nucleus 2, so that's quite unusual. And what's also very unusual is that these odd integer plateaus are quite strong. Okay, to explain this, we need to look at what are the expectations of a quantum Hall effect from a topological insulator. So the topological insulator has two Dirac nodes, two Dirac fermions, one on the top surfaces and the other one on the bottom surface. Okay, each of these gives rise to something that's called a half integer quantum Hall effect. Okay, due to the presence of the zero level half field. So this is what I'm showing here. Is the Landau levels for a single Dirac count in a perpendicular magnetic field. Okay, so for 3D topological insulator, where we have so this should produce filling sequences n plus 1/2. Okay, this 1/2 is special for Dirac nodes. And if you have a topological insulator where we have a bottom and top surfaces, so we have two of these Dirac nodes, we get this degeneracy factor of 2. So 2 times n plus 1/2. So then you would calculate it that the filling factors nu that you should see in this quantum Hall effect that I just showed you, you should only get odd integer plateaus, right? So 0, you can work this out. Okay, but this picture, so normally in a 3D topological insulators, you would expect only odd plateaus. Okay, so this already gives you a hint why we have these very strong odd integer plateaus. But this picture doesn't take into fact that we have heterostructures where the two surfaces are not really at the same potential. Okay, so that's what I've indicated here. So if you go back, for example, on one side of the heterostructure we have aluminum oxide, on the other side we have the 3,5 semiconductor. So this is a very asymmetric heterostructure. So unlikely that these two Dirac nodes are at the same potential. If you have this potential shift, you get something what I've shown here. So orange are the Landau levels from one of the surfaces, and purple from the other surface, and you get these intersecting and crossings. Okay, and that explains why we get, for example, why we get these unusual filling factor sequences. So in the middle here, in the intermediate magnetic fields, you can see, for example, here this very strong nucleus 3 plateau, but you can see how some of the even ones might be absent because you have this, you're close to these crossings, and so they're poorly resolved. Okay, so this picture of this 3D TI, what you expect in the case of having a offset in the surface potential, explains exactly what we're seeing, and it also explains the 3D TI states, why we get a quantum Hall effect in such thick films, okay, where we wouldn't really expect yet any quantum confinement effects and subband levels, okay. So these films are 45, 50 nanometer thick. We wouldn't expect yet a strong confinement effects, okay. And it also explains why we get relatively thickness independent filling factor sequences, okay, because independent of 45 and 50 nanometer films will both have the same types of topological surface states, okay? And it's also consistent with the theory of cadmium arsenide. So the picture here is a slightly different way of showing this offset in the surface potential. We have these band crossings here. Blue is our cadmium arsenide that has inverted bands. We resolve this going to the normal materials such as aluminum oxide and 3,5. And it requires these Dirac fermions at the interfaces, but the interfaces are a little different, so we get this slight energy offset between them. So this topological insulator picture completely describes our quantum Hall effect. And so the next things is just next couple of slides is just an additional study looking at the thickness dependence of these quantum oscillations. In case of I'm a little bit short of time, but in case of quantum confined box states, you would, for example, for different thicknesses, you would expect these are the subbands, okay? And as you go through different film thickness, you would find these oscillations of band gaps and no band gaps. And basically, without going into the details of this, what you would expect is a very strong thickness dependence of the Shubnikov-Dyer oscillations if they came from these quantum confined subbands, which is not what we are seeing, okay? Let me skip this slide. But rather, if you look at films sort of in the thickness range between 12 and 24 nanometer, look at tune the carrier densities to be identical between these films, you can see the Shubnikov-Dyer oscillations are look rather identical despite us having varied the thicknesses. So this confirms what I just told you about the interpretation of the quantum Hall effect. We have 3D TI surface states here in these films, which explains the thickness independence and the sequences in the quantum Hall effect. Okay, and it also means for fairly thin film thicknesses down to 12 nanometer, we still have this 3D TI state. Okay, so I wanted to briefly talk about something a little bit more practical and what are potential applications of these materials. There's a huge number of applications, and this is by potential applications that people have been looking at. And this is by no way a very complete slide, but just to give you a little bit of flavor of what kind of applications people look. There's a lot of suggestions for optical applications, nonlinear optical applications. They're very strong nonlinear optical effects. For example, collaborators in Japan have used our films to show that that there's very strong terahertz generation via higher harmonics in these films. It's actually more efficient than graphene. This is largely because cadmium arsenide is thicker. There's spintronics applications because of the spin polarized surface states, for example. There's topological superconductors for quantum computing is a potential applications. But the one I wanted to talk about just a little bit with the remaining time is to look at high frequency applications, okay? So for transistors. And the motivation for this is because cadmium arsenide has a very high Fermi velocity, okay? It's actually, if you look at this table here and compare saturation velocities of different semiconductors as well as Fermi velocities of different 3D TIs, vowel semimetals, and also graphene, it actually has the highest Fermi velocity. Okay, so that promises high-speed applications. Okay, in particular in scale devices, which is much more important than the mobility is actually the Fermi velocity. And the other important things, if you think about transistor applications, is also how much charge you can accommodate. So speed is important, but also how much charge you can accommodate. So for example, 3,5 semiconductors, which have very low masses, have actually trouble accommodating a lot of charge because they have a single minimum in the conduction band. And there's other important practical considerations that contact resistances must be low, and RC time constants become important with small transistor gate lengths. Okay, the challenge, of course, with cadmium arsenide, it's not a semiconductor, it's a semimetal, so there's no band cap. Okay, so this applications that require a completely off state will, of course, be difficult. And this also means that there's no saturation in occurrence. And what I just showed you, so even if you open up a band gap in a Bach, you still have these gapless surface states. Okay, so that's one of the challenges with making electronic devices with these materials. Okay. Right. So, but just let's look a little bit at the basic channel properties and as a channel material for transistors, and it turns out they're very, very good. So at room temperature, for example, we can get charge densities around 5 times 10 to the 12. This is quite good. What is especially good are the extremely low contact resistances. Okay, so in this device, this particular device, it's actually better than most 3.5 contact resistances. What is also very, very attractive are the extremely high current densities. So in this case, in narrow channel devices, we could actually get current densities up to 10 amps per millimeter, which is very, very high. Okay, and that is the reason is a relatively high charge density, but also the high velocity in this material. Okay. So you can take these measured parameters that I just showed you and sort of estimate what the frequency property behavior of a device that uses cadmium arsenide as a channel should be. So they have a circuit model here for the device for a MOSFET type of device where we have a gate dielectric, okay? And orange is the cadmium arsenide channel. And I just gave you numbers for the sheet resistance. We can calculate the velocities from the data I just showed you, and we had sheet carrier densities I just showed you, and we can estimate the capacitance to the density of states, and you putting all this together into the circuit model. This is what my student Omar did, and estimate what the cutoff frequency FT, okay, should be for cadmium arsenide. And so these results are quite encouraging. So you can see that this cutoff frequency reaches even for small devices where our C delays are significant into the terahertz regime. Okay, so that's very high. And there's other attractive properties. For example, there's normal semiconductors that has something to do with the parabolic bands of normal semiconductors. There's a drop off at high carrier densities in that cutoff frequency. That will not happen for cadmium arsenide, and this is something to do with the Dirac electron properties. Okay, and you can also maintain these very relatively high cutoff frequencies to fairly low charged carrier densities. That's, for example, important if you're concerned about heating effects and so forth. Okay, so these are calculated properties. Okay, so this is not measured properties, but they're based on the experimental measured parameters of these cadmium arsenide channels. And so here's, of course, one should check once it gets in the experiment. So here's the first results from making transistors out of cadmium arsenide. As expected, we get very high current densities, okay, that I already showed you here, and that are could be pushed higher, it's going to higher voltages. The current modulation is moderate, and this is largely due to the fact that we still have carriers in a Bach that are not responding as well to the gate voltage. But the other big problem, and this is some separate study that I cannot show you because of time constraints, is interface trap density between the gate dielectric, which is aluminum oxide deposited by ALD in this case, that these interface traps is large. So the gate voltage largely modulates the trap density rather than the carriers in the channel, and that reduces the charge modulation in the channel, and that results in a reduced transconductance. Okay, but estimates, if you would reduce these trap densities, you can estimate it at least get a factor of 10 improvement in the transconductance, and already this transconductance is actually quite good. Okay, so this initial results without optimizing things like interfaces between the gate dielectric and the cadmium arsenide are actually quite promising. Yeah. So with that, I'd like to sum up my talk and just mention a few of the points I was trying to make. So what I wanted to show you is that cadmium arsenide is a very good platform for creating different topological phases, which of course each of these are interests which I couldn't get to for different types of applications. We get actually a very good topological insulator state with transport, it's really only through the surface state. So unlike some other candidates for topological insulators, where the transport was often, the bulk was not very insulating, and you got a mixed, in electrical transport measure, mixed transport through both surface states and the bulk. This is not the case here. So we have really, it's really quite a good topological insulator once you open a band gap. And it's relatively easy to open a band gap by, for example, applying strains or confinement. Okay, it has a very good tunability, so it responds nicely to a number of things. What I showed you is strain and confinement. And so we can, for example, use this strain, for example, to get even larger gaps. And I showed you to even further minimize the transport through the bulk states, which is important for the transistors, but also, for example, if you want to apply them as topological insulators. Right, and I showed you that really we have a very nice description of our quantum Hall effect and the thickness independence of the Landau levels that really confirms what we should expect for 3D TI. So it's very nicely behaved also in that way that we really have this 3D TI model to describe the transport, what we are seeing. And very briefly, I showed you actually at least one example for potential applications. Of course, there's a huge number of other applications for quantum materials and some of them making more explicit use of the quantum properties. But even here in these high frequency applications, what I wanted to show you, there are unique properties of these Dirac electrons. Just the high frequency performance that are different from conventional semiconductors, and that have barely been used or even realized for applications. And with that, I would like to thank you very much for your attention, and I'd be happy to take questions.
Questions? Do you have any questions? Claudia?
Maybe I start. Thank you, Susanne, for this very interesting and nice talk. I have a question concerning the first part. So you showed nicely that you can do quantum confinement and get the 2D topological, the 2D quantum Hall effect with the surface state. But since you have also thicker films, did you also look for the quantum oscillation in the thicker films and the 3D? Because nowadays people, because of zirconium telluride 5, are interested in 3D quantum Hall effect. This would be nice whether you see a transition from the 2D to the 3D if you become thicker.
So we did, I'm trying to find a slide. We actually looked for the 112 films. We looked at Chubnikov-Tehase oscillations, and you can see they're there for the 2D states. To fairly high thicknesses. We did not really look if our interpretation. So there's no quantum Hall effect because there's huge, bulk carriers here. So we don't really have a clean quantum Hall effect for those. But we do see the Chubnikov-Tehase oscillations from those surface states, even to fairly thick films. The problem being here that there's like a lot of power conduction from bulk, so there's no clean, quantum Hall effect for these very thick films. So our picture is really, at least for the 112 films, that the surface states are always there, and we can get the Chubnikov-Tehase oscillations. I would be hesitant to go further than that and say there's at some thicknesses there's the bulk, Fermi loops type of Y orbits type of physics involved here. So it's a little bit of an open question for us.
Another question? More questions? If I may ask a question, in the part where you tune the properties with the tensile strain or the compressive strain, the strain is on plane, right? I mean, you are not compressing along the thickness of the film.
It's an in-plane biaxial stress, but of course the strain is triaxial. So if we apply a compressive strain in the plane, it expands out of plane by.
And it's an isotropic strain you apply.
Sorry?
Is an isotropic strain you apply the same in all directions, or?
It's in plane, yeah. So in plane, it's a biaxial strain, the same, and then out of plane, it's dictated by whatever the the elastic constants say. Yeah.
We have a question from our online viewers, and it is: what do you think about calculate the lattice parameters with Debye-Scherrer equation and Bragg equation to analyze the interaction between cadmium and arsenide in cadmium arsenide?
I don't quite. So I'm not quite sure if I understand the question. So we know the shape of the unit cell. Is the question more from X-ray as well as from convergent beam? Is the question more about the atomic structure, how it changes on the strain?
I'm not sure. Maybe if it was asked by Catalina, if Catalina can send us a message and clarify a little bit her question. Let us wait. So meanwhile, if there's another question for... Claudia has another one.
So also quantum anomalous Hall is now in the focus of research with this manganese tellurium bismuth telluride. So is there a way to have integrals of manganese arsenic or something in cadmium arsenic to get a similar good quantum Hall, anomalous Hall system here, to get magnetism into the cadmium arsenic? Do you think about this, or do you have some?
Yeah, I've thought about it. Yes, I think there's a few studies out trying to dope it. I feel I've not heard anything that it has worked out. The other way of so doping chromium, I think I heard is not working. The other and there's others, a number of other possibilities of introducing dopant atoms. What is I think probably maybe more promising is to interface it with other materials. So there's some very interesting magnetic ones out there. Europium cadmium arsenide is a magnetic Val semimetal. So maybe via interfaces and heterostructures, I think there should be very interesting possibilities of making new heterostructures, combining magnetic materials that are lattice matched. Europium cadmium arsenide is pretty well lattice matched. There's also europium indium arsenide. So there's definitely good candidates for making heterostructures, and definitely I think it's in the future of these studies is not to stick with just a single material, but actually combine different materials and heterostructures.
More questions for Susanne? No? Well, I may just take this opportunity to ask Susanne and Claudia if you want to submit a symposium for next year on topological and beam metals, you're welcome. and I think there's a diploma for you that I think they are going to project now. I mean, since you're not here, there's, I'm sure they will send it to you, but if we don't have any more questions, let's thank Susanne for this nice talk, and thank you again for accepting the invitation.
Thank you for having me.
Well, thank you all, and I think we can continue with the other symposium right now, no? There are other sessions. Thank you. Okay.